Now let's talk about density altitude and what that means to us as general aviation pilots. Density altitude, of course, refers to the density of the air. Exactly how dense is the air? How close are the air molecules together? Well, when the air molecules are very close together, then the air is more dense. When the air molecules are spread apart, the air is less dense. Now, for us, that means that when the air molecules are close together, such as when we have high pressure, a high altimeter setting, and low temperature air, then we would have a low density altitude. And when the air molecules spread farther apart, that is because we have higher temperature air or a lower altimeter setting. So high temperature air and low pressure or low altimeter setting leads us to a high density altitude. And of course, increasing our elevation also decreases the air density. The air is naturally less dense the higher we go in altitude. Thus, when we have dense air, we call it a low density altitude, as if we're at a lower altitude. And when we go up in elevation, we call it a higher density altitude. Think of density altitude as the feels like altitude for the airplane. We have the feels like temperature, maybe it's 90 degrees outside, but it feels like 95 because of a certain few atmospheric conditions that make it feel warmer, and the same thing applies to the airplane. You may be here in Ohio, where you're actually 1,000 feet MSL, but the density altitude, the feels like altitude to the aircraft, is 2,000 feet based on the pressure altitude and the temperature. Remember, density altitude is nothing more, the true definition is just the pressure altitude corrected for non-standard temperature. All right, so when we set our altimeters to 29.92 inches in our cockpit and we read what the altimeter says, that is our pressure altitude. And then we correct that for the non-standard temperature, whatever the temperature is outside. That gives us our density altitude, and our E6Bs are a great resource for doing that. An example of low density altitude would be when we read a METAR report like this in Detroit, where we see colder temperatures and higher altimeter settings, and we know we're at a low elevation in Detroit. Well, then we have a low density altitude, and the airplane will perform well because there is more air for the wing, there's more air for the propeller, and there's more air for the engine to breathe and burn with the fuel to make power in that engine. When we go to a place like Denver here, and we have warmer temperatures and higher elevations like Denver, and also low altimeter settings, well, then there is less air to flow over the wing, there's less air for the propeller to push against, and there's less air for the engine to breathe and burn with fuel and make power. Looking at this takeoff here out of Telluride, Colorado, with a density altitude of over 10,000 feet, well, we can see that our takeoff roll, instead of 6.5 seconds at a 2,000 foot density altitude, now this takeoff roll is substantially longer, even though the airplane is at the same exact gross weight. Now, this doesn't just hamper our takeoff roll or increase our takeoff roll when we have high density altitudes, it also kills our climb performance. We know that our airplanes don't climb as well at 10,000 feet as they do at sea level. We have performance charts in our POHs that tell us this, but if you don't have that POH handy, or perhaps you have an airplane that is so old that the POH doesn't give you all that data, well, we can use something that's very helpful called a koch chart. And as we come here to the koch chart, we can see here that if we draw a line from the actual temperature that we're experiencing right now, say on the runway, this is the temperature, we'll draw the line across to what our pressure altitude is when we set our altimeter to 29.92, we read that altimeter and it says, say, 5,000 feet, and our temperature outside is 80 degrees Fahrenheit, we draw that line between the two, and we can see the impact that is going to have not only on our takeoff roll, how much extra runway we will need, but we will also see the impact it's going to have on our climb performance. It's going to make the airplane climb much slower. So we have these multiples here that increase our takeoff distance and also decrease our climb performance, decreasing our rate of climb, meaning we're not going to have great obstacle clearance as we take off of a high density altitude airport. Keep in mind, while this koch chart is very helpful, it is not a guarantee. Each airplane's a little bit different. For example, I have an old Cessna 140 with an 85 horsepower engine that, despite what the POH says, it can only climb to 8,000 feet at gross weight and not go any higher than that. If I tried to use the koch chart to figure out what my rate of climb would be at, say, a 9,000 foot density altitude, it's not going to give me accurate information because, quite frankly, my airplane can't go above 8,000 feet density altitude, period. And our service ceilings and absolute ceilings that are published in our POHs, those are altitudes that are based on standard pressure and temperature. So really the density altitude is going to be how high you can go. Say your airplane tells you, oh, the service ceiling is 14,000 feet. That doesn't mean you can get your altimeter all the way up to 14,000 feet. If it's a hot day with low pressure, the airplane may only climb to 11 or 12,000 before not having enough power to climb any higher. The biggest dangers we have with density altitude is it causes our airplanes to perform in a way that we're not used to, especially if you're used to flying at sea level or on colder days with higher altimeter settings, and all of a sudden the density altitude changes rapidly because you go to a different airport or the weather changes. The airplane will not perform the way you're used to, and the normal climb attitudes you use are not going to perform the same way. You're going to always be using more runway to take off and land and be taking off and landing at higher ground speeds when you have higher density altitudes. Some important considerations to take into account are things you can do to decrease the effect of this, such as removing weight from the aircraft, taking out excess cargo, and trying to lighten your load or perhaps leaving a passenger behind, and also waiting to fly either in the morning or later in the evening when temperatures are cooler and the density altitude decreases. Of course, density altitude for a given pressure and a given airport elevation is going to be the worst right around mid-afternoon when the temperatures are highest. Lastly, we'll talk about humidity, because humidity also affects the density of the air. Now, how much it affects the density of the air is really hard to say, but we often will say if it feels very humid out, you should add at least 10% to all those other numbers. So increase your takeoff roll by 10%, decrease your takeoff rate of climb by 10%, increase your landing distance by 10%, and so on. And that's a conservative round number. Sometimes it's more, sometimes it's less. But humidity, the water molecules in the air, actually force the air molecules to spread out even further and cause the air to be less dense, again, providing less performance to our aircraft.